in StreamYard.
Yay! Hello, everyone. My name is Eric Mattson. I'm a professor of computational biology at Fred Hutch. And I'm very lucky to be joined by Nina Salama, who is also a professor at Fred Hutch and is also the head of MCB, the Molecular and Cellular Biology program at UW.
And Fred Hutch. Uh-oh, Eric, you froze on me.
I'm still here.
Oh, good.
Do you want to say a word or two about your work?
Sure. So I'm a microbiologist, cell biologist, lots of different things, and I study a pathogen called Helicobacter pylori that infects the stomach and is the biggest risk factor for stomach cancer. So we do a lot of host pathogen interface types of studies using various infection models. And we generate some data that could be analyzed computationally, but I am a computational neophyte.
That's awesome. So you'll notice, so Nina already said, like, she's not here to provide computational expertise. She's actually here because Nina always asks amazing questions. And so I figured, when I thought of, like, who would I want to have ask questions, for a bit of a tour of the command line, I thought definitely Nina. So she's going to be here to ask questions, but I don't want there to be a power imbalance here. So I want Nina to go ahead and ask me the easiest questions you can imagine about microbiology or molecular biology, just to show who's boss.
Well, Eric, you do a lot of analysis of DNA sequences, I know. And I was wondering, do you know how Sanger sequencing works, which is kind of the gold standard of sequencing?
Is it with, like, oh, no. I don't think I do. I mean, I know in the old days, you'd have, like, these termination nucleotides, and then you would run it on a gel.
Oh, you're pretty good. So what is it? So normal, what are the normal nucleotides used by DNA polymerase?
Oh, they're nucleotides?
Yeah, they're deoxyribose.
Okay.
Right? And the termination nucleotides have another oxygen. They're dideoxy.
All right. We're going to call that a fail and move on. So now we've set things. So the way this is going to go is I'm just going to give a little quick tour, some slides, and then I'm going to do a bit of a demo. So let's go ahead and start with some teaching goals. First, I'm going to describe what high-performance computing is and why we need it. I'm going to talk a little bit about command line interaction, and then how to run a command in parallel across cores. Oh, and I did want to, before we get started, so anybody can ask questions on YouTube. We've already had 2 comments from Rossi and Kate, so this is awesome. So please post your questions, and then if I don't see them, then Nina will read them. Okay.
Excellent.
So, this is a fact. If you're doing large-scale computational analysis, you're going to outgrow your laptop. So you can't just, like, keep on running stuff just there. And when I showed this slide to my wife, she said I had to put in this, which is a ferret that has clearly outgrown its housing. So you need to expand into a larger world. And here's a larger world. This is what a modern data center looks like. We'll talk a little bit more about what they look like here in a bit. So this is just, this is what the Fred Hutch has. It's got about 500 compute nodes with 2,600 compute cores, 2 petabytes of storage. This is kind of old, but these are big numbers. And we'll talk about what these numbers actually mean in a bit. And so there's a lot of compute power, and typically we use Linux to access this compute power, but there are other tools such as Galaxy. So Galaxy is a wonderful, wonderful tool. It basically allows you to have simple interfaces to powerful tools, which is good. And I don't want this to be a slight on Galaxy, but to a certain extent, it's a little bit like this. It's a little bit like having a mix, and you can do one thing with a mix. You can make the mix. Here's German chocolate cake, but if you want to do something different, you're sort of out of luck. And so even if you sort of want to go to all recipes and download a new recipe, something that's not sort of known to Betty Crocker, you need to have a proper kitchen and be able to cook things up on your own. So Linux really, if you know how to deal with Linux, you can do whatever you want on high-performance compute systems. It's complete freedom. So let's talk about what those compute systems look like. I don't know, maybe this picture looks boring to you, Nina, but to me, this is just like, whoa. So each one of these rows is like a unit in some high-performance computing system. Like this is like a big compute rack. I think this is a bunch of drives over here. Anyway, there's a lot going on here. Yeah.
So in the movie Hidden Figures, the IBM computer came in, and it was pretty big and took up a lot of space, kind of similar to this. Like, how does this compare to those early computers?
Oh, poof. Your phone would just crush all the computing power in the world. I mean, you can buy like chips that are like a penny each. I mean, it's not like, I actually don't know the movie you're talking about, but if it's one of these old like
this was the one about the black women in NASA that like were part of the computation to get Apollo to the moon.
Sounds awesome. I should watch it, though. I should warn you, I watch about one movie every 4 years. So
maybe another way is like, eat one of those little bars, like the black one.
We'll unpack that. We'll unpack one of those. Yeah. But just so these are big computers that require a lot of cooling. So this is actually just for our data center at the Fred Hutch. This is just one of the vents that the air goes through to cool. So everything is set up so that the air goes in one side through the computers and out the other side. And Fred Hutch has like a pretty cool setup. But if we're talking about something like what Amazon or Google has, oh my God, like the scale is just insane. So yes, Nina, let's unpack one of these things. So this is one of these rack-mounted computers. This is actually a relatively old picture because this is a spinning hard drive, like people don't use that much of anymore. But in any case, and this is a CD-ROM drive. Here are two fans that are fanning. This is the main processing unit. Oh, you can see my cursor. And this is a power supply. So this is to supply power to the processor. So the processor sits underneath this sort of copper thing, which is, again, to take the heat away from the processor. So this is a somewhat modest one of these things. But it's probably, if you had a modern one, it would have multiple processors. And each one of those processors would have somewhere between 20 and, 40 cores or something like that. I mean, sometimes like the Hutch is using a lot of 4-core machines as well, which can be useful. Anyway, this, any one of these is going to be way more powerful than your laptop. And you see that there's sort of racks and racks and racks and racks of these things. So when you sort of add all that together, it ends up being a lot of cores. So let's just talk about cores for a second. So this is what a processor looks like. I've actually been spending surprisingly large amount of time thinking about this L3 cache recently, which is sort of like a very, very fast memory. And then these up here are the cores. So each one of these cores is sort of like a processing unit. It can do computations independent of the other cores. And so when we're talking about how many cores the Fred Hutch has, it's each one of these processing units which gets combined together onto one of these chips. And this is sort of the appropriate time to describe how we should think of these as independent processing units, not just as making things faster. Like a very naive view is like, okay, well, if I can throw 2,600 cores at a problem, it's going to run 2,600 times faster. And that's not always true. So I'll just make a little metaphor here. So here is a situation where they added more capacity, so more engines. These are actually helicopter jet turbine engines, and it actually just made the whole thing faster. So this is a tractor that's powered by helicopter jet turbines, and it's like going 4 times faster because there's 4 of these things. And so that's actually not the right mental model for having these powerful computers. It's much more like this, where we have 4 of these harvesters that are like plowing or like cutting the wheat out of the field, And it's not one harvester that's 4 times faster. You just have additional capacity to mow a lot of fields. And so you have to, like if you're a farmer, you have to be very strategic. So if you're very unlikely and the field that you had to harvest was extremely skinny and very long, you'd have to be thinking about how am I going to orchestrate all the different tractors or the different harvesters so that they're using their resources intelligently. Whereas, I mean, it would be a lot easier if you just had one super fast tractor that could cruise across it. But that's not what we have. You have just sort of lots of these things. And so one of the things we'll address, and not today, but eventually in the course, we'll address how do you sort of deal with doing lots of different things at once in a relatively easy way. Okay. Any questions?
So I have a question.
Yeah.
So the fact that you have these different sort of parallel processing units, do you also have to think about the timing? Like, like are they all going to operate at the same speed or, do the same thing? I mean, I guess you would have to, like, if you need an output of one thing for the next, that timing obviously is important, but do they behave pretty uniformly?
Yeah, you don't want to depend on them having to behave uniformly, for sure. So there's definitely lots of strategies that people use for sort of having sort of like a lab protocol where it's sort of like, I have this, and then it feeds into this, and then it feeds into this other thing, and so on and so forth. So those are called workflow managers. The most classic one is known as make, or just a shell script. We'll be talking about shell scripts a little bit later. But there's a lot of cool new work happening now. We've started using Nextflow recently, and it's really great. And so that sort of allows you a very flexible control of, like, we have all these things, and I'm just going to tell you what needs to feed into what, and then you go figure out what to do next. So it's an important topic. And I don't think one that will really cover a lot in the class, but I'm happy to provide materials. Okay, so we talked about high throughput compute. This is high throughput storage. This is just sort of an example of what large storage looks like. Each one of these is sort of a unit that houses a hard disk, and this is known as a RAID configuration, which is like a high redundancy setup where one of these can fail and you don't lose data. And so what the amazing technology that happens here is that we can throw just zillions of hard drives into these things and then treat it all as just sort of one big hard drive. That's pretty cool.
Hey, okay. Erica, there's a comment in the chat that I don't understand. It says cores versus threads.
Yeah, so let's see. So a core is a physical unit on a CPU like we're talking about. A thread is a software level concept that allows you to leverage cores more effectively. So basically, when people talk about multi-threaded computation, they're saying it's using an operating system level construct called threads and saying, operating system, here's a bunch of different things I need to do. You go do them. And then the operating system figures out, I see I have all these different threads that need to get executed. I'm going to say, okay, thread 1, you get core 1, thread 2, you get core 2, and so on and so forth. So oftentimes when we're talking about doing multi-processor execution or multi-core execution on a single machine, we talk about multi-threaded execution. But in order for that to be effective, we need to have multiple cores for those different threads to run on.
So just a follow-up question on that is in the instructions of the job, are there instructions embedded within that help the core? I mean, how is the operating system smart enough to know how to make those assignments?
So I'll just tell you, Nina, I'm running on a laptop and like we're doing this thing, but there's other stuff that I'm getting email, like, you know, the Dropbox maybe is doing something like ever since, you know, I don't even know, like this has been a central goal of computer engineering for a long time. Be able to do lots of different things on a computer simultaneously without having them block. Like the fact that you and I can have this conversation and I could just start my music player and it would start working seamlessly is just mind-bogglingly amazing engineering. So we really can't go into that, but just to say that like we're interfacing with this tremendously sophisticated thing. Like the multi-threading that happens on your phone, just crazy. You're making a call, you're watching a YouTube video, and you're checking your email at the same time. Like that's amazing. It's not as amazing as Helicobacter. I'll give you that.
But I guess what I was wondering is how much of that is just the operating system knows what to do, and how much of it is in the whatever the
both. It's really
okay,
both.
So it's a two-way communication.
So there are some problems that people call embarrassingly parallel, where you're sort of just like, I need to like analyze 15 files. We can do those in whatever order happen. Just tell me when it's done. And those are really easy to multi-thread. There are some things that are like almost impossible to multi-thread. So if you have a process where everything in your computation depends on all the previous computations, that's basically impossible to multi-thread. So that's sort of like a generally hard problem. And it's something that like I write a lot of software, and we think a lot about that because computers aren't getting a lot faster, but they're getting bigger. They're having more, it's easier to access more and more compute power in terms of like the number of harvesters, not in terms of actually things getting faster. They are getting faster, and it's amazing if they are, but not as much as they're getting bigger. Okay. So the command line is the computational lab bench. So we're going to be talking about the command line today. It's not the place where you do your most amazing fancy stuff. At least I hope it's not. But it's the place where you like propose, like you prepare the samples, and then you take the sample and you put it on the fancy machine, right? Like you have your like super duper sequencer or like a high power microscope. So I sort of this is my image of what happens in the wet lab. Like she's got all of her colored liquids and she's squirting them into the thingies, and then she's going to put it on the microscope and look at it. And this is like, I think, a totally appropriate mental model for like what the command line is. Like you shouldn't you shouldn't be thinking like, of course you're not like taking out individual pieces of DNA on your bench and like doing stuff with them. No, you're like preparing them for the fancy machine that does the thing. So the fancy machine is a program that might be something that somebody else wrote, like SAMtools, or it might be some R analysis that you did, or it might be some machine learning thing that's happening in Python. So like, just keep that in mind, that like what I'm about to tell you, this is not like a general purpose programming language. It's not something you're supposed to like get a lot, like do some hardcore computation in shell. You're just preparing the samples to be handed off to some other cool tool or to synchronize the computation like Nina's talked about.
Hey, Eric, I feel like the metaphor for this is more like actually like the protocol. Like, actually it's like what you do in your lab notebook where you're saying like, okay, this is the sequence of events. This is how everything's going to fit together.
Well, I would say that that's more of a shell script.
Okay.
The command line is an interactive environment that you can do stuff with, but then you can also automate it using a shell script. Cool. Thanks for the questions. I love it. Okay, so the command line is this native environment for interacting with Linux, and there's also similar environments for Mac OS and Windows. So I think Mac OS people are now quite familiar with. There's this thing called the terminal, which you can run. So because you open a terminal does not mean you're running Linux on your computer. It is a similar environment. A lot of the same commands that I'm going to be talking about are present. It's a little bit different. I don't know, maybe it's a Coke versus Pepsi sort of thing. Windows has the PowerShell. That is quite different than either, like it's Mac OS and Linux are much more similar than PowerShell is on Windows to either of them. But now you can run this thing called the Linux subsystem for Windows. I have no experience with it, but it is a proper Linux environment for you on Windows, which is pretty neat. So all of those commands should work there. Yeah.
I have a question. So what is the difference between Linux and Unix, which is what I use back?
Yes. Okay. In the beginning, there was Unix. So Unix was, I don't know. I mean, like, I honestly feel like Unix is one of humanity's great achievements. So there were all sorts of crazy, terrible operating systems before Unix. And then some geniuses, and I don't use that word lightly, like at Bell Labs came up with Unix, and it seems so obscure to us now. Like what I'm going to show you, you're going to be like, why? It's so complicated. But trust me, what happened before Unix was way, way more complicated. I've had a great time listening to podcasts and talks about like what happened before Unix and the development of Unix. So Unix has this beautiful, clean interface with some nice principles behind it, and we can talk about them. Like, you know, you write programs that do one thing and do it well. You write programs to work together, and you write programs to handle text streams because that's a universal interface. And so, like, this philosophy is so powerful, but it was like a huge leap forward in usability from the previous generation of tools. So, but Unix is a proprietary thing, and it had to do with AT&T. And then it just so that sort of doomed it. Like it was expensive, and then this very clever person called Linus Torvalds was like he was bored over Christmas break and decided he didn't like that Unix was pay, and so he decided to write his own Unix, and he called it Linux, which is Linus's Unix basically.
Got it.
And he started giving it out to his friends, and like. Now, I don't know what the estimates are for how much it would cost to redevelop Linux from scratch, but I mean, it's just like the billion. I think it's not an exaggeration to say that right now, as far as high performance computing, there's Linux and rounding error. It's the only platform that anybody actually uses. Microsoft really made a play to try to be a competitor, but it's just not. So it has taken over the world, and Linux is basically a from the ground up rebuild of a Unix-like system, and it's continued to evolve. And Unix, there's BSD Unix, which still continues to exist, but its market share gets smaller every year. So.
Got it.
Okay, I had a slide that said that I think Unix is like one of humanity's great achievements, but I took it out. But you asked the question. Anyway, okay. So to use the command line, you issue text-based commands, and let's just talk. These do have a type of grammar. So let's say we want to buy eggs. So if I was not being very polite to you, Nina, and you were at the store, I would say buy eggs. So we have like the verb, which is the thing that is to be done, and then I don't know, I guess this is a direct object that's associated with that action. But in English, we also have ways of sort of giving modifications to commands like this, like subordinate clauses or prepositional phrases or something. So like I could say, buy, using cash, eggs. Or buy 2 dozen eggs. So we put those things in the middle. And so in the same way, when the command line, we say buy, and then we have these modifiers, which we call flags, and then we still have eggs. So flags, you can recognize them because they have 2 dashes. There's sort of some extra space here, but it's just dash, dash, dozens, eggs. And sometimes they have 1 dash, sometimes they have 2 dashes, but anything that sort of starts with a dash is going to be some sort of modifier in it. God help you if you decide to name your file something beginning with a dash, because you're just in for a world of hurt. It'll always interpret that as some sort of command line flag. Not recommended. So if we have multiple things, we might say buy using cash 2 dozen eggs. So here we have our dozens 2, and then we have like using, and then we put in cash. And so in English, you would have some rules where you sort of would say buy 2 dozen using cash eggs. That wouldn't really make sense. But in Linux, it doesn't matter. Like you can put this using cash in front of dozens 2 typically. Like typically, you can just reorder these sort of modifying flags arbitrarily.
So another question here. So the dash dash tells you that it's then the next thing right after the dash is the thing, and then there's always just one object. So using
No.
cash, you can't do like
Yeah.
using cash or credit.
Um, Typically, it's space delimited. So I mean,
Hmm.
like, there's lots of command line interfaces out there, and there's unfortunately, it's not super standardized. But if I was
Okay.
going to say, I don't know, yeah, cache and something else, and want to combine that into maybe it's like cache and wallet. I would design it so that you have cache, comma wallet is one thing with no space between it. Uh, but typically it's just one space delimited unit after a thing. It gets, I mean, people, like I say, there's no rules. Like when you write one of these things, you're literally just parsing this thing. So people can do whatever they want. But I would say that's a convention that you sort of usually have a flag and then you have some space delimited word, meaning like something with no space in it that is the argument of the flag. Okay. And yeah, so sometimes we don't actually need an object or something like that. So you might have multiple different arguments at the end as well. So this is one of the really amazing things uh, about these Unix-derived interfaces is these things called pipes. So the idea is of a pipe is that we have something that's from this first command and it gets passed to the second command. So here we've bought some eggs. Now we have the eggs. So buy eggs returns eggs in some form. And then this pipe says, take that stuff and pass it to this next command. So here we have it's getting passed to a frying pan. Um, and any questions about that, Nina? Does that make some sense?
Yeah, that's kind of cool.
Okay. So there's actually one thing I wanted to point out here is that you can see oil doesn't have a number after it or anything. So you can have flags that just like are a flag. They just modify behavior of frying pan, even though there's no argument that's associated with them. Yes, Cecile. Hi, Cecile. I haven't seen Cecile in years, so she's tuned in to say you shouldn't put spaces in your file names either. And so at this point, it should be pretty obvious. Like if I wanted to like I wouldn't want to call something organic space eggs. Like then you would be confused because you would be thinking buy organic and buy eggs. No, 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 no. Maybe we'll look at that a little bit later. But yeah, I mean, so this is definitely a pain point with our dear biologist collaborators, where sometimes they want to use strange symbols and or spaces in their file names, and it makes our life more difficult. Okay, so not only do we have sort of the ability to pass things between commands, we can also redirect them into files. So this isn't a perfect metaphor, but basically what's happening here is that sort of we have a command that's running, and then it gets passed over and stored using this thing. And this is supposed to represent like an arrow, right? Like it's not supposed to be greater than. It's supposed to be I am taking that stuff and like mapping it onto the plate. Like it's getting sucked onto the plate with an arrow. So here we have buying eggs, frying them, and storing them on a plate, which I mean, we should think about it, storing it as a file. It's a plate. Okay. So we can write a little program, like you said, like to automate these things. This is called a shell script. So here's what a little shell script might look like, where we start by buying eggs. They get passed to our hands, and we want to crack them, and then that goes into a bowl. And then we so that gets stored in bowl. Now we have stuff in the bowl. We can whisk, and we're saying the input to our whisk is going to be the bowl, and we're going to pass that to the frying pan, and then eventually it's going to get to the plate. So we are going to come up with like a 2-line shell script next that will hopefully illustrate these concepts. Okay.
Wow.
Wow, Nina, what do you mean? Wow.
We're programming already. This is just like, I'm excited.
Okay, so Nina, as you're looking at this, how does this make you feel?
This isn't so bad. There are a lot of backslashes, but I'm okay.
Okay, so let's talk about backslashes. So yeah, I'll make it bigger because I can see you're leaning in. Let's make it really big. And um, so this is covered by the course material, which is sort of a self-directed thing. I'm not going to go into depth about this. This is just sort of an overview. But this is what it looks like if you log into what are called one of our Rhino class computers at the Hutch with a totally stock configuration. I'm not giving you my hot rodded configuration here. And what this is telling us is that we're in a folder that's called TFCB 2020. And inside that, there's another folder called lectures. And inside that, there's another folder called lecture 02. And that's where we are. And another way, if we want to see the full thing, you can see here, if we do this command called pwd, then it tells us where we are. And so all the directories, they're called, in Linux speak, they're called directories, and I won't be able to avoid that. But just think folders, if that makes you feel more comfortable, is this. And so you can see that all I did to execute the command was just type it and hit return. And like, I don't want this to seem scary, so like, I'm just gonna like mash the keyboard and like nothing bad happened. All that happened is it was like we didn't find those commands. So like, there are some things you can hurt yourself badly by removing things, but if you mistype a command, nothing's going to blow up. Nobody's going to be sad. So that was a very simple command, pwd, that just returned a value. But also, so let's do one of these things that has a sort of an argument. So this is cd, and tilde is like the base of your home directory. And so this is sort of the equivalent of your desktop, I guess, or your home inside your file system. And we can ls, and that tells us basically where we are. This should feel a little bit like I don't know, maybe I'm dating myself, but there used to be these like text-based adventure games where you would type in like, open the door, step in. So this is sort of like a text-based adventure game for nerds. So this is when I ls from sort of my base, you can see that there's one directly called compost and another called tfcv. So if I want to, well, let's see.
Hey, what's the $$ for?
That is just saying, this is the end of your prompt. And so there's all of this stuff, and this is just telling you that's the end of this. And so start typing here. And I am going to bring up my little hot roddy configuration here, just to show you that it's not, yeah, I mean, it's rather small, but like, so these things vary, right? Like, it doesn't have to be a $. It can be colorful and have all sorts of fanciness on it. But that's one convention that people use. So just very briefly getting around, use CD, and so the pedestrian way to
change drive or
change directory.
Okay.
So the pedestrian way is to type in the whole thing like that. And that's quite tedious. We don't like tedious. So the fast way is to tab complete, which I'll present in a second. If we want to go back a directory, we do cd ... So that's sort of back one directory. So the faster way to do it is do cd tf, or even just t tab. And tab sort of looks at what are all the things that are accessible to which I can tab complete, and then takes the one that starts with what you have. So if you start by nothing, you can still tab complete. It looks a little confusing here, doesn't it? Because these hidden things have shown up. We better just forget about that and just say, press T, and then it'll start tabbing through. But actually, here's a better example. Lectures, and then now I can type, let's see, lecture And now I can tab complete, and it shows me all the different lectures, and I can pick one. So I'm going to pick O2. There's also cool things you can do, like CD tilde and then CD dash actually jets you back to where you were before. I don't know. Like it gets totally fancier. Like if I was going to do this on a nicer setup, I'm not. I don't know. Maybe this is counterproductive, but I'm just like it gets even fancier where you can just say J. Like for me, I have this auto jump thing set up where I do J TFCB, and it knows, oh, you probably mean it remembers where I've been in the file system and tells me it sort of jumps to that place. There's also this other thing where it's like,
oh, somebody in the chat here has translated a bunch of these commands for us.
Oh yes,
Thomas.
Thank you, Thomas. Anyway, yeah,
super
anyway,
helpful.
it gets fancier, so I'm not. That's all I'll say about that. Okay, so yes, Thomas.
And just one more thing, Eric. I mean, you just know this language, and so you know all these things. But like Thomas has translated this for us. So is there like a little cheat sheet of like the most important, most used?
Oh yes, and yeah. So this is sort of just the intro. Like this is just getting people familiar with typing things in. All that stuff is part of the course material. This is just sort of an overview. But yeah, Thomas, a good point. PWD means print working directory, CD means change directory, and LS means list files in the current directory. Yeah. Okay. So what are we going to do here? So I'm LSing. And so I'm going to CD to something called scripting. And here I have a bunch of text files. And actually, here's a nice... So there's ls, which tells us what things are. If we're interested in... how about this? I was going to do it differently, but let's ls and then pipe to something called file. No, that doesn't work. Okay, we can do file. So this star, wow, this is sort of hard to parse. So this tells us what are the file types of all the different things. So there's this text. It'd be easier if it just said text, but it's just text file, another text file, and then this is a script file, and this is a gzip compressed data. And so this is what's known as a BAM file, which is a very common format, a binary format for dealing with genomic data. And while I just am thinking of it, there is helpful online help, which is known as MAN. This is short for manual. I don't know. You can tell, like, we can have a discussion if this is chauvinistic. But MAN file, is the way to get to the manual. And so what we can see here is it's showing us these are all the different flags. Like, this isn't saying that you should put all of these options on at once. Oh my God, I actually want to do this now. But this is saying here are all the different flags, just so you know them. And then if you want to know them, so I actually don't know much about file, but I'm guessing, so then if I'm interested in, okay, what does this V flag do? Okay, so that V flag, then I do a /, which is search, and then -v, that's going to take me to, it just prints out the version. So if I do file V, it's going to print out the version. And here it is, the file 5.32. So that's just, again, a really quick intro to MAN. Okay. Just for clarity, because this is a huge, long thing, I'm just going to do this /. Well, I hate to do something weird. Anyway, there's a tool called SAMtools that's going to allow us to look at this binary file. So I can say SAMtools view, and then so I'm double tabbing because I've forgotten what everything is. WGS, and this is my BAM file. So I could hit return, but it would just barf all over. So what this is going to do is SAMtools view is going to just write all of that information that's in that BAM file out to the terminal. And that just like would not be all that fun. So I can pipe it to this thing called less. So remember, this is like we're taking like the eggs and mapping them to the frying pan with this pipe. So we're taking all that crazy output that's coming from SAMtools view, and we're going to put it in this command called less. And so a less is a pager. Ooh, oh, right. OK, this is good. So there's this. So I forgot that SAMtools isn't sort of natively accessible. I need to do this thing called module load. So I can do module load SAMtools. And now I can do SAMtools view. But actually, before that, there's something else I didn't talk about that's just as cool as tab completion, and that's this reverse search. So I do Control R, and then I start typing something like ML, and it tells me all the different previous things that I have done that involve ML. So I do reverse search ML, and then I just keep on doing Control R, and it's going to show me all the different things that I've done for ML. So that's handy because these things can get complicated. So where we were going is I was going to take SAMtools view and then pipe it to less. And so now we can see our all of the information in this. So this is a little out of my wheelhouse. I don't deal with BAM SAM files very much, but I'm pretty sure this is a bunch of reads that somebody had, and they mapped them to the human genome. So this is what the reads look like. And this column here is the chromosome number in the middle.
Oh, so that's chromosome 1.
Yeah, and if I type big G, that's going to take me to the very end. And this is chromosome star, which I think could just mean unmapped. But we're actually going to look.
So how do you get the headers? Like, how do you, like, you happen to know that column was the chromosome, like, but is there a way that you can get what the headers are?
So this is a little bit embarrassing, but man, SAMtools is broken on right now, and I've filed a support ticket. But you would just say SAMtools help or like man page. But actually, there's a beautiful version. It's actually worth going to the web for this because SAMtools has beautiful, beautiful documentation. Yeah, here's the man pages. I don't even know. You can just sort of click through it. Let's see. I should be looking for view. How about SAMtools view? Perfect. OK, so here are the different things. So then I would look for a column. Well, yeah. I think there's some sort of. Here we are, Nina. Great. OK, include the header in the output. Let's do that. Nope, that's not the right one. Where do I want to go? Here. So I can go back to the beginning with Control A. SAMtools H. Ooh. Oh, maybe it's SAMtools view H. It's always good for the presenter to sort of like mess things up. There we are. So this tells you that. Wow. Well, I'm definitely out of my league here. I'm not sure exactly what all is going on. I think. Yeah, I don't know. Somebody else knows something about SAMtools, and I sure don't. Include the header. Output the header only. Maybe it's thinking of header as being something else than I am.
Okay. Well, so theoretically, there's a way to do it, but you just happen to know that column referred to the chromosome.
I'm sure the people are going to be berating me on the chat here in a minute, just telling me, how could you possibly not know that?
It's pretty quiet over here.
So if I'm only the little exercise that we're going to do is to just extract those the chromosome numbers, and so there's this other command called cut. So cut, like remove sections from each line of the file. And so you can do cut and then F3. So that means take just that third column. And so let's type that to less again so we can take a look. Whoa, this is different than... so somehow... Oh, yeah, it's because I still have this H flag on. And for those following along at home, if this looks tedious, and it is tedious to click through everything, but if you do control, it sort of takes you a word at a time through it. Okay, this looks better. Okay, so another thing about less is sometimes it does this wrapping thing like what we're seeing here. So this is actually just like, this is one line, and this is one line, and this is one line, and that gets annoying. So you can do less S, and then that makes it so you can click back and forth. If we really care about those crazy question marks and things, we can go to the end with our arrow keys. But okay, here we are. The third column is the chromosome number. So I'm going to say cut F3 and then pipe that to less. Oops, less. So you can see I'm making typos, but it's okay. Nothing bad happens.
There you got it.
Okay. So now what I would really like to do is to count the number of occurrences of all these different reads. So I'm curious about, like, we have a bunch of reads that are mapping to different chromosomes. How many reads are mapping to each chromosome? So there's sort of a canonical way to do this is first we want to sort the reads according to their chromosome, and then we want to pipe it to this thing called unique. And then unique has this flag called C, which says just like, so natively, yeah, we'll just do this, unique. So unique just tells me all the different unique things that it got mapped to, but unique C counts them like this. So I guess I should pipe that to less again. So here we are, there's 438 reads mapped to star, which maybe is just unmapped. And then 4593 to 1, and so on and so forth. So that's kind of cool, but it's a little bit annoying that it's ordered. Like I'm curious about. I want to see like what are the most important things at the top. So what are the things that get
mapped the most?
Got mapped the most. So then I can say. Actually, let's do it in 2 steps. So what I'm gonna do is first I'm gonna count to. I'm gonna do this counting, and I'm gonna map it to a file. So, like, give me a file name, Nina.
Apple.
What?
Apple.
So this is a great teachable moment, Nina. Apple is an entertaining name. However, it's not an informative name. And if I was to later come back and encounter a file named Apple on my computer, I would not know what it was. So how
about read counts?
Yes. How about
chromosome read counts? I don't know.
Chromosome counts. So what's wrong here?
You got a space.
Okay, I can go to sleep a happy man.
Underscore, yeah.
Okay, chromosome counts. So now actually we can use less in a different way. We can look at this chromosome. We can give less an argument instead of having information flow in from the outside. And so now I can less this file, which means I can just go back and forth in it and look at it. Another way is you can just cat the file, which means splurt it all out to the screen, but that's sort of annoying because we can't see the top anymore. Okay, so now that we have our lovely file, chromosome counts, we want to, let's say we want to sort it. So we can do a sort of this file by just saying sort chromosome counts, because remember I want to like sort it in terms of the number of counts. Mm-hmm. And I'm just going to say, so head just gives you the first several lines. So This is sorted in a certain way. It's sorted, but weirdly, like it's 1 and then 0, and you can see that it's like 1 and 0 and then 1, but 11, like this is a bigger number than this. It's sort of sorted in terms of strings instead of in terms of numbers. So I can just say man sort, and one of the options is in a numeric sort. Okay, so now I can sort this. Okay, and that's okay. That's better, but it's going from bottom to top, and I want to go from top to bottom. Okay, now we're in good shape. Okay. So now we have the biggest number at the first. So we can see that chromosome 2 had 464,600, whatever. 4661 reads map to it. And so instead of just doing head, I'm going to say sorted chromosome counts.txt. Okay, so let's say that's all of what I want to do. Now I want to make a script that's going to do this. It's not going to be like a very general purpose or like wonderful script, but it's a script. And so for that, there's this thing called history. So this is a very common thing that I do if I'm coming up with a shell script. I just do it one time and then I save it so that I can replay it later. And if I need to generalize it, I can do that as well. But here we're just going to save it as if we needed to do it again later. So there's this thing called history, which tells me all the commands that I've run, the good ones and the bad ones. And I'm going to get the tail of it, which is the opposite of head. So I just want the most recent one. So I'll take the last 20 commands, and I'm going to pipe that to script.sh. And so now I'm going to edit this and go in and clean out all the commands that I didn't want. So one way, so there's lots of editors available. The simplest one is called Nano, but it's pretty user-friendly, I guess, but it's so limiting that we actually even stopped teaching it. But if you really forget everything and you need to just look or make a small modification of file, it's okay. But so I can just type things and use the arrow keys like you would expect. So now I do Control X, and I'm going to say no, don't save. And we are actually sort of, I mean, you can use whatever you want, but we have been teaching VI, which is a very, very, very powerful and quite arcane editor. It again has lots of commands you just have to know. DD deletes a line. But you can also do this great thing, which is visual mode V, and then it's like selecting things. It's like selecting things in Word or something like that. And let's see, so I want that. So I'm going to go there. What else do I want? This was good. Okay, this is how we got the sorted chromosome counts. And there's lots of fancy ways that you can delete things in Vim. So here I can just delete that word. I can also do sort of a fancy block version of the selection and delete like that. Okay. So like when people talk about a shell script, it sounds sort of fancy, but actually all it is just a list of commands. And it does have variables. It does have other things you would expect in programming languages. But I encourage you not to use them to their full extent. Like use shell scripts for running collections of other commands. Yes, use variables. But once it gets past a certain level of complexity, it's really time to reach for either one of these workflow project managers or workflow managers, or something like a general purpose programming language such as Python.
So just to be clear here, Eric, so what you have now trimmed this down to is 2 commands, right?
Yep.
And this thing has a name, and so now you can run this?
Yes, so let's do that. So to get out of Vim, you have to do this, like you do this thing. Again, this is covered in the course material, but the :W which is for write and quit, you can also put it to sleep by doing Shift ZZ, and that puts it to sleep. So the way I initiated this session was by saying VI script, and so that took me into the interaction mode with VI. And so now we can see that I've ls that there is this script.sh, which is there. So that's our file. And if we want to run this now, so let's just say, well, yeah, okay, I've named this something else. So I can say rm, and so this is another piece of sort of fanciness. I can do star counts.txt, and so this means like remove everything that ends with counts.txt. So one should be careful with this. I have carefully looked, and there's nothing else that I don't want to remove. And so when we ls, like those counts.txt are gone. So now I want to run my script. So one way of doing that is just say sh script.sh, like so. And now I can ls, and there they are again. Mm-hmm. We can see that it did the same thing. Another thing we can do is change it so that it's an executable script, so that I can run it a little bit more like I would run a normal program. And that has to do with changing the execution bits. So here I have ls.l. And so ls.l is sort of a more informative way of running ls. It also tells me about these things over here. It tells, and these things determine what sorts of things I can do with this. But the point in this class is that this one has a bunch of X's. And you can see it has a nice green color. That means it's an executable script. So we can do that to this other script by saying chmod a plus x script.sh. I mean, it doesn't get a lot more arcane than that. So chmod stands for chain. I think it's change. I don't even know. Change module file mode bits. I mean, change file mode bits. That doesn't even make. Oh, change mode, I guess, is probably what it's short for. Change mode. Yeah. Yeah. Anyway, now we can see.
Now it's green.
Now it's green. And so I can just run that by saying script.sh. So I like to use PureShell. Other people like to use bash. But if I wanted to use bash, I would do another arcane thing, bash, and say, it's another sort of shell type scripting. Oops. And,
all right, you're kind of going too fast now.
Well, I should just stop. I mean, yeah. I mean, the point that I'm trying to make is that a script, all it is a bunch of commands that you combine together into a file.
Right, and then you can call it out as that, and there's a couple different ways to do it.
Right, and I think we're kind of we're out of time. I think that's all I really wanted to say. Don't overuse shell programming. If it gets too complicated, do something. And I hope you will be a happy and free ferret.
With a cool sweater.
Yeah.
This was fun. We started broad, we dove in and got messy, and then we came back out the other side with cute ferrets.
Awesome. Well, thank you so much, Nina. It was really a pleasure to hang out with you.
I think I should take this class. It seems fun.
You need to talk to some departmental administrators to see if you're eligible. All right. Have a great day.